Hi, I'm Chris Van Allsburg. You may have read some of the children's books I've written, Jumanji, Polar Express, or Zathura. In this episode of NASA Connect, you'll learn about the history, mythology, science, and math that relates to a total eclipse. NASA scientists and engineers will introduce you to a satellite that actually makes its own false eclipse. In your classroom, you'll build an eclipse simulator. So stay tuned as host Derek Wang takes you on an exciting journey, NASA Connect, Path of Totality.
Hi, I'm Derek Wang, and welcome to NASA Connect, the show that connects you to math, science, technology, and NASA. On today's show, we're going to learn about eclipses and angular size. Teachers, you'll want to make sure your students are ready for some critical thinking. When these questions appear on the screen, you'll want to pause the videotape to facilitate class discussions. Today I'm at the Museum of Contemporary Art in Santa Rosa, California. This is the home museum of Daniel Alberti, sculptor of the stars. No, not movie stars, those stars. Everyone, I would like for you to meet Daniel, who has created many unique sculptures using celestial mechanics. Celestial mechanics is the mathematical calculation of the movement and positions of the planets and other objects in the sky. Daniel even has a personal connection to the sun. Isn't that right, Daniel?
Well, that's right, Derek. But everyone has a connection to the sun. I'm a sculptor, and I like to use the light of the sun and the light of celestial objects to play off the surface of my work. As a young boy, I would often ride my bike over to the California Academy of Sciences to check out the Morrison Planetarium. They had great shows on astronomy, and there was this fantastic pendulum which showed how the Earth rotated on its axis. These are the kind of places that inspired my interest in astronomy and the mysteries of the sun.
Daniel, our show today is about eclipses. What can your sculpture tell us about solar eclipses?
As an artist, I'm fascinated with light and shadow. I love the way light changes during the course of a day, depending upon the position of the Earth to the sun. So I began to sculpt objects that show light and shadow on their surfaces. And over here is a sculpture I recently created. It's my favorite.
That's cool. What is it called?
It's called a shadow catcher. This bowl-like structure focuses natural light as a dot drifting across the sculpture. Watch as the dot passes across the shadow catcher. It's interesting to see how the form travels along the surface of the sculpture, much like the shadow of the moon crossing the Earth's surface. And students can make their own shadow catchers. For directions to make the shadow ball, check out the link at NASA Connect website. Of course, an eclipse is one of nature's most dramatic works of art.
Daniel, thank you very much for sharing your personal story with us.
You're welcome.
Okay, so did you notice Dan uses science and math to create his works? His understanding of form, light, shadow, and space are what makes his sculpture so unique. Let's find out more about these magnificent solar eclipses. Here at the Chabot Science Center in Oakland, California, visitors can explore interactive exhibits that teach about the movements of the planets and their moons around the sun. The movement of the Earth and Moon creates the most powerful display of form, light, shadow, and space in our world, a total solar eclipse. As a total eclipse begins, the moon's shadow approaches from the west. The chill and the sweep of the moon's shadow rushes across the landscape at over 1,600 kilometers per hour. Totality is a phase of the eclipse when the light from the sun is completely blocked from view. The darkness of totality resembles evening twilight affecting living things. The sky near the horizon still appears bright, but sunlight seems gray and weak. The solar eclipse is an amazing sight. But to understand what an eclipse really is, we need to talk to a NASA scientist. But before we do that, here are some questions that your students might want to think about. Why do eclipses occur? What is angular size? What is the path of totality? Why don't we see a total eclipse every moon cycle? This is a great time to pause the tape and discuss these questions. Fred Espenak is one of the world's authorities on eclipses. He works at NASA's Goddard Space Flight Center in Greenbelt, Maryland. He uses computers to make predictions on thousands of eclipses, and he runs NASA's official website on eclipses. These accomplishments and his participation in dozens of eclipse expeditions have earned him the nickname Mr. Eclipse.
So let's ask Mr. Eclipse, how can something as small as the moon block out something as big as the sun?
Good question, Derek. A total eclipse of the sun is one of the most awe-inspiring sights in all of nature, and it's all made possible due to the unique geometry in the distances and sizes of the sun and moon as seen from the Earth. As we all know, the moon orbits the Earth and the Earth orbits the sun, and celestial mechanics allows us to calculate these orbits with great precision. When the moon passes between the Earth and the sun, we say that the moon is in the new phase. An eclipse of the sun can only occur when the moon is new. However, not all new moons produce a solar eclipse. The moon's orbit around the Earth is tilted about 5 degrees to the plane of the Earth's orbit around the sun. As a result, the moon spends most of its time either above or below the Earth's orbital plane. The moon passes through the plane only twice during each of its orbits. If the moon also happens to be in a new moon phase when it crosses Earth's orbital plane, then a solar eclipse will occur. Most eclipses are partial because new moon takes place just before or after the moon crosses the orbital plane. But if the timing is right, a total eclipse of the sun occurs just as the center of the moon passes directly in front of the center of the sun. The path that the moon shadow makes over the Earth during a total eclipse is called the path of totality. To see a total eclipse, you must be in the path of totality. As a total solar eclipse begins, a ghostly silhouette looms into view, framed by a white glow that creates a halo around the darkened sun. In the final seconds, the sun's remaining rays shine through deep valleys along the edge of the moon. At the same time, the sun's corona appears, surrounded by the moon's black disk. Before the last bead of sunlight vanishes, the effect resembles a cosmic diamond ring. Suddenly, totality. The bright sun is gone. A black disk surrounded by a pale halo now stands in its place. The sun's corona is the most stunning, most beautiful, and most unexpected feature of a total eclipse. As the outermost layer of the sun's atmosphere, the corona is extremely hot with a temperature of 2 million degrees Celsius. The moons of other planets in our solar system produce eclipses, but none of them have the perfect size fit that total eclipses have from Earth. In some cases, the moons have angular sizes that are much larger than the sun. In other cases, the moons are much too small and too far away to cover the sun. We call this kind of an event a transit. Our NASA Mars rovers have both photographed Martian moons Phobos and Deimos as they transited the sun. Pretty cool. To compare the relative sizes of the Earth, Moon, and Sun, we'll use this basketball and this tennis ball. Let's call this basketball Earth and this tennis ball the Moon. These are the relative sizes of the Earth and Moon to each other. So what do you think we could use to represent the size of the sun? A small car? Think bigger. The sun would be 90 feet in diameter, about the size of this office building. So how is it that this tennis ball-sized moon can block this building-sized sun? The answer is angular size. Angular size is the measure of an angle formed by extending imaginary lines outward from a specific point to span the width of an object. The imaginary lines form a triangle. Angles are measured in degrees. Two objects in space may appear to be the same size if their distances and diameters are proportional, and if they are viewed from the same position on Earth. The diameter of the sun is 400 times larger than the diameter of the moon. But the sun is also 400 times further away from the Earth than the moon is from our planet. If you extend imaginary lines that span these two objects to our viewpoint on Earth, you can see that two similar triangles are formed. The angles formed at the viewpoint are the same for both objects, making the angular size of these objects equal. When these bodies line up exactly, the moon appears to be the same size as the sun, creating a total solar eclipse. This fortunate coincidence is responsible for the perfect fit of the total solar eclipse, one of the most spectacular events you can possibly witness in our solar system.
Thanks, Mr. Eclipse. Now we understand much more about eclipses.
Let's see if students at the Challenger Learning Center in Bangor, Maine can help us demonstrate just how important angular size is to an eclipse.
Permission to come aboard, ma'am.
Permission granted.
Hi, welcome to the Challenger Learning Center of Maine.
NASA Connect asked us to show you this very cool activity.
We created a model to show how one object can eclipse another.
Teachers can download this activity at the NASA Connect website at connect.larc.nasa.gov.
To do this activity, we had to use measurements and proportions to determine distances and diameters, understand how two objects in space with very different sizes at different distances appear to be the same size, measure the angular size of two objects, and measure an angle. We followed the directions from the NASA Connect website lesson guide to make our eclipse simulator using a shoebox, paper, tape, scissors, and a skewer stick. We had to use our geometry skills to find the center point on each end of the box. Then we drew a horizontal line along the center of each side of the box. At the center of one end, we punched out a small hole about 2 centimeters round. We used this as our peephole to view the objects in space. We traced the lighted end of a flashlight over the center of the opposite end of the box. We also traced a quarter on black paper and cut out the smaller circle. We measured the diameter of each circle and recorded them in our journals. Then we attached the smaller black circle to the center of the skewer stick. We set up proportions for similar triangles to help us simulate an eclipse. We know that the diameter of the larger circle divided by the distance from the peephole to the larger circle is equal to the diameter of the smaller circle divided by the distance from the peephole to the smaller circle. Once we understood the relationship between these values, we had to decide which value we needed to find. Since we already know the diameter of both circles and the distance from the peephole to the larger circle, we need to calculate where to place the smaller circle from our peephole. We set up a proportion to solve for that value. Once we came up with a number, we measured the calculated distance from the peephole and slid the skewer stick in place. We added string to demonstrate how the angular size of the objects was the same. The string helped us see that the distances and diameters were actually sides of similar triangles. We used a protractor to measure the angle formed by the string. We were able to use the same proportion to predict the diameter of an object even farther from the peephole. We checked our solutions by making a circle with the predicted diameter and placing it between the strings at a specific distance. Our small circle was able to eclipse an even larger object. The proportion helped us prove that angular size is related to the actual diameter of two objects and the distance they are from a specific point. We even covered our flashlight in yellow cellophane to demonstrate the sun's corona when we had a total eclipse. Of course, we took safety precautions and used dark sunglasses to look at the flashlight. This was just a simulation. We know you should never look directly at the sun, even during an eclipse.
That was sweet. Now I understand how the moon can block the view of the sun. But why is it so important to study the corona? I guess I need to learn a little more about the sun. Let's visit with Carolyn Inge of NASA's Sun-Earth Connection to learn more about this very important star.
Hello, Derek. You're right. The sun is very important to all of us here on Earth. Our sun is actually a very average star. It is not the brightest nor the hottest star. It's actually classified as a dwarf.
Heat and light come from deep within the center of the sun, where nuclear reactions between the gases release massive amounts of energy. Like Earth, The sun has an atmosphere surrounding it. Because the sun is so bright, it is hard to see the upper atmosphere of the sun. But when a total eclipse occurs, the moon blocks out most of the light from the sun, and the corona is visible.
As NASA looks deeper into different parts of the sun, we gain more knowledge about the Sun-Earth connection. We know how important the sun is to us all.
Heat and light generated by the sun make life on Earth possible. Variations in the sun's temperature could have dramatic effects on Earth's long-term weather. Solar storms affect satellites, telecommunications, electrical power grids on Earth, and are a danger to astronauts. The sun even holds clues to how we can generate renewable energy for future generations.
So studying the sun is extremely important, and a total solar eclipse gives scientists a dramatic way to study one aspect of the sun, its corona. Back to you, Derek.
And now you understand more about eclipses in the sun. I wonder if ancient people understood eclipses as well as you.
Here are some questions to consider. What did ancient civilizations think about eclipses? Can eclipses be predicted? Let's talk with Dr. Sten Odenwald from NASA's Goddard Space Flight Center to learn how people develop their own special stories to explain eclipses.
Eclipses have long been a source of mystery. These events were often viewed with fear and awe in the past. Today, eclipses still thrill us. The ancient Chinese once believed that an eclipse of the sun occurred because a dragon was eating the sun. The Chinese would produce great noise, such as drumming or banging on pans, to frighten the dragon away and bring back the sun. A similar story is a Native American legend of the Choctaw Nation, attributing an eclipse of the sun to a mischievous black squirrel who would try to eat up the sun at different intervals. The Egyptian pharaohs believed they were the representatives of the sun god Ra, and the iris of an eye is often seen in their artwork, such as the Eye of Horus. Similarly, the ancient Nazca culture of South America believed that the sun and the moon were the separate eyes of the sky-dwelling gods. There is a very good reason for this belief. A total solar eclipse bears an uncanny similarity to an eye in the sky. The hole in the sky formed by the black disk of the moon mimics the pupil of the eye, while the rays of the sun's corona resemble the iris of an eye. Ancient cultures around the world have drawn this same symbol. At about the same time the Nazcan culture in South America recorded their eclipse, the same eclipse may have been witnessed by Philostratus in Italy. He wrote, "There appeared in the heavens a certain corona resembling the iris, surrounded the orb of the sun, and obscured his light." It's interesting that Philostratus used the term corona, which is the Latin word for crown. Today, astronomers still use that word to refer to the outer atmosphere of the sun. The ancient Greeks once feared eclipses, but fear turned to reason when a Greek-Turkish philosopher by the name of Thales used deductive reasoning to predict an eclipse.
According to some historians, Thales was the first person to study solar patterns to accurately forecast an eclipse. The date was May 28, 585 BC. His prediction of darkness in the middle of the day actually brought an end to a 6-year war fought between two cities. Thales carefully studied the patterns of the moon. To do this, he used records left by the Egyptians and Babylonians. His prediction earned him a place among ancient historians as one of the 7 wise men of ancient Greece.
Thales understood how angles were related and the properties of similar triangles. He might have set up simple proportions to determine when the Earth, Moon, and Sun would line up again. Thales may also have known that every 18 years and 10 days, the Earth, Sun, and Moon are in the same geometric relationship. This is called the Saros cycle.
This means the same lunar phase happens on the same calendar day. Thales might have known when the last solar eclipse occurred in his geographic region from records kept by the ancient Babylonians. By adding multiples of the Saros cycle, every 18 years and 10 days, he could have predicted that a new moon and eclipse would reoccur on May 28, 585 BC. Some people thought he was a powerful magician, but Thales may simply have been using observations, historical records, and a little arithmetic to make his famous prediction. By always asking why and how, Thales contributed to the development of science and mathematics. Every time we observe a pattern and predict an outcome, we follow his example. Today, we know enough about the orbits of the Earth and the Moon to predict eclipses. Some people take special trips to watch a total solar eclipse. NASA has a team ready to observe and record the total solar eclipse in Turkey. In 2006, the path of totality travels from South America to Asia, where these ancient peoples once lived. And when viewing an eclipse, make sure that you wear proper eye protection. Sunlight is so bright during an eclipse that it can damage your eyes. Back to you, Derek.
Today, scientists at NASA have devised ways to create eclipses all the time. Can you think of a reason why scientists would want to create an eclipse of the sun all the time? Let's meet with Steele Hill of NASA's Goddard Space Flight Center SOHO mission.
SOHO is a spacecraft that is closer to the sun than we are. It observes the sun from 1.6 million kilometers from the Earth. SOHO stands for Solar and Heliospheric Observatory. On board, 12 instruments gather information about the internal structure of the sun's outer atmosphere, and solar storms. There is no other spacecraft like it. The sun's magnetic field appears to be responsible for heating the corona and producing violent explosions called coronal mass ejections, or CMEs. CMEs carry billions of tons of charged gases into space, and CMEs can reach Earth in 1 to 4 days. To observe a CME, SOHO has two telescopes called coronagraphs. Circular disks in the coronagraph block out the sun to create an artificial eclipse, allowing NASA to observe the corona. Scientists watch clouds of plasma blasting out from the sun as flares or CMEs. SOHO takes images about every 20 to 30 minutes and sends these images to the Deep Space Network here on Earth. The images are processed and displayed on the web within 30 minutes after traveling 1.6 million kilometers. CMEs are one type of space weather that can set off electrical surges in power lines and create radiation danger for astronauts. Scientists worldwide are using SOHO data to learn how to predict space weather that could endanger the future explorers of our solar system. Although we scientists have the advantage of seeing eclipses every day through SOHO, nothing can replace the personal connection people feel when they observe a total solar eclipse here on Earth. Its profound effect links us back to the ancient peoples before us.
Our researchers remind us that an eclipse is more than just the sun, the moon, and the Earth. Each of us has a personal connection to the sun. Even our biological clocks are set to the light-dark cycle charted by the Earth's movement around the sun. Carolyn Ng has a special guest with her to help us better understand this sun-Earth connection.
Hi again, Derek. We are here at Chimney Rock, Colorado. I would like to introduce to you Dr. Shelley Valdez, Science Educational Consultant for Native Pathways. She's also a tribal member of the Pueblo of Laguna.
Tullis understood that knowing how the moon moves through the sky is a key to predicting a solar eclipse. The Earth has a slight and slow wobble off of the ecliptic, which is the pathway of the sun and the planets as seen from the Earth. The ecliptic pathway is easiest to learn as it is seen upon the backdrop of the stars. This wobble causes the moon to rise a little further north and a little further south on the horizon over a period of 18.6 years. This movement of the moonrise over landmarks on the horizon appears to slow and then stop for several moonrises before the movement starts going the other way. The point at which it appears to stop is called a lunar standstill. Ancient Puebloans were avid observers of the brilliant night sky of the elevated Colorado Plateau on which they lived. They learned to time events throughout the year according to when a star constellation, the sun or the moon rose or set on the horizon. They also learned to build observatories that served the same function. At some point in time, it was noticed that the full moon rose between the two spires of Chimney Rock during the northern lunar standstill every 18.6 years. Ancient Puebloan rock drawings recorded eclipses. We know that an eclipse was important to the ancient ones because of the record they made on the rocks. Like the Nazca, the Egyptians, the Turks, and the ancient people everywhere, similar circular designs were used. Ancient people were divided by oceans, mountains, and deserts. But through their art they left behind, we know that eclipses were events which linked all people together, as it continues to do so today.
Today we continue to watch the passing of the sun and the moon in the sky.
Every year close to the spring equinox, a special solar event is monitored by scientists, students, and educators. People are brought together by celestial events such as total solar eclipses and the transit of Venus, as well as staged events called Sun-Earth Days. One of Sun-Earth Days' main goals is to provide an opportunity for you to learn more about the sun's connection to the Earth through images, cultural parallels, and activities. NASA's Sun-Earth Connection collaborates with schools, science centers, and museums around the world. We produce webcasts and other resources.
Thank you, Carolyn. Thank you, Shelley. Thank you, Alex.
You're very welcome.
Well, we really learned a lot today.
About eclipses, how they work, and how they affect people.
I would like to leave you with one final challenge.
Are eclipses or transits only caused by a moon's shadow on a planet? As our astronauts travel to the moon, Mars, and beyond, will they encounter any other object in space that may have the same angular size as that of the sun? Are there other relationships that might create an eclipse?
Conduct your research on the internet, and you can work together to find an answer. And you can get back in touch with me at NASA Connect. Well, this wraps up another episode of NASA Connect. We'd like to thank everyone who helped make this program possible.
Got a comment, question, or suggestion? Email them to Connect.
So until next time, stay connected to math, science, technology, and NASA. Goodbye for now.
Hi, my name is Mary Sanchez. I work for NASA. I'm also a member of the American Institute of Aeronautics and Astronautics, or AIAA. We can help your students learn how math and science are used in everyday life. For more information on how to request a mentor for your classroom, please visit the NASA Connect website.